Hello, everyone. Hey, so I want to put together a little review video for you students in Chem 26, the class I am substitute teaching for. So let's go over some problems I've chosen from the sample test. You should probably do all the problems in the sample test. That would guarantee the highest chance for doing a good job on the upcoming exam. But I thought, you know what? With this online learning, I thought maybe I should at least go over some on a video, and hopefully that'll be helpful. Of course, the answer key is provided where I work out my solutions. And if that's enough, that's what I was thinking. Maybe this video would be helpful to you. So here's some here's some problems that I've chosen to work out, and hopefully it's helpful. Okay, so the top of your exam will look something like this, beginning with the equations and data. So there we go. So for the sample test, I got this verbiage up here saying, yeah, the sample test is way too long. It won't be as long as this on the real exam. All of this information will be at the top of your exam with the periodic table. So that's information you don't have to memorize. You will be given this information. Okay, so let's just start with number one. Don't have time in this video to do all of them, but this first one's pretty good. So let's do a couple of these. This will be in a multiple choice format. Some of them will, some of them won't. For the ones that are not multiple choice, be sure to show your work because I give partial credit. And after the exam's over, then you can upload your work as a PDF. Okay, so which of the following will not produce buffered solutions? Okay, so what this is asking, first, do you know what a buffer is? Buffer is something that has both a weak acid and a weak base in it. A buffer resists changes to pH. It's actually kind of cool. So you have this solution, and in it is a weak acid and a weak base. And because both of them are weak, they don't neutralize each other. Instead, the weak acid sets up an equilibrium, the weak base sets up an equilibrium, and they're just there. And if some goofball dumps in some strong acid, well, then the weak base attacks it and neutralizes it. And if you had the same solution with both the weak acid and weak base present, and somebody's messing around and dumps in a strong base, well, then the buffer's weak acid will neutralize that incoming base. And in that way, the solution tries to maintain its pH. It's kind of important. It's essential for life. So in fact, our blood is buffered by bicarbonate ions. One molecule serves as both a weak acid, an H+ donor, and a weak base, and it can accept an H+ too. So, if you eat an orange or a lemon juice or have some lemonade, that's quite acidic. Or eat, a salad with Caesar salad dressing, or Italian dressing with vinegar in it, that's acidic. That could lower the pH of your bloodstream and cause death. Ouch. But no, it does not happen because your bloodstream is filled with bicarbonate ions. So as the acid from vinegar, lemon juice, whatever, this is a weak base and attacks it and neutralizes H+. And if you happen to eat something that's a higher pH, well, the buffer donates its H+ and neutralizes it and tries to maintain the pH. Essential for life, kind of cool. Solutions, do you get a buffer? And read the question carefully because I might change it on the exam. It might say, hey, which ones do produce buffers? This one says, no, which ones don't? So what's going on here? Well, you've got so much of this thing. Yeah, what is that thing? Well, what you should do is know some things about some acids and some bases. So let's list those. Things you should know, things you need to memorize. You should know the strong acids. And they are the halides, not fluorine. Fluorine's a weak acid when it's combined with H. So HCl, HBr, HI, and you get a periodic table. At least I think you do. Where'd it go? There it is. Yes, you do. You get a periodic table on the exam. And your halides are over here in column 7A. Fluorine's the exception. Most electronegative atom. It's a weak acid when paired up with hydrogen. But chlorine, bromine, iodide, HCl, HBr, HI, strong acids. What else do you know? There's 6 of them. So we got 3 of them, HCl, HBr, HI. The others are nitric acid, sulfuric acid, and perchloric acid. There's a 4 in both of those. These all have O's, and then NSSCl. That's something to know. So that's a way to memorize the strong acids. Strong bases, those are pretty much bases made from hydroxide ions. So alkali metals, NaOH, LiOH, KOH. If you go to alkaline earth metals, column 2, like calcium hydroxide and magnesium hydroxide, those are not very soluble. So they can't really be a strong base. So there you go, those are your strong bases. The basic anions. Okay, well, so there are other anions. Hydroxide is definitely one of them. Hydroxide anions are very basic. So sulfur, it's right below oxygen on the periodic table. And then, let me make sure I got all 6. But there's carbonate, let's get a little room. There's carbonate, there's a bunch of C's. There's carbonate ion, which is basic. There's chromate, which is basic. And there's oxalate, which is basic. And then there's one more, phosphate. Yay, I remembered them. Those are all basic. So if those show up, those are weak. Well, this one's not. Hydroxide's not a weak base. It's strong base. The other ones are weakly basic. So if you have salts like sodium sulfide or potassium phosphate, the solutions will be weakly basic. The pH will be above 7. And then acidic anions, acidic cations, they have to be H plus donors. So they have to have some H pluses. They are the amines. I don't know if you've heard of those, but the ammonium ion. And so start with that one. Start with the ammonium ion. It has an extra hydrogen. Nitrogen prefers 3 bonds, but it's making 4, so it can donate an H plus. And then if you exchange or substitute a hydrogen for carbon, so there's 4 hydrogens here. How about we take one of those hydrogens away and bring in a carbon with 3 more hydrogens? That's also acidic. The nitrogen's again making 4 bonds. It has extra H. It can donate H plus donors or acids. And then the other thing are, where's the book? So if you go to the book, they're cations of metals that are highly charged, like aluminum, iron, where's the list? There we go. Iron, copper, zinc are examples. Basically, things that are not group 1 and group 2, alkaline metals and alkaline earth metals. Yeah, go away. The idea is that the metals that are highly charged, like aluminum +3, they actually are so highly charged and water's polar, water will make a covalent bond to them and form these coordinate complexes here. And then what will happen is one of the attached water molecules will actually release an H plus. And so which one is it here? It looks like the top one. So this top, I can't try it on the screen. This top hydrogen is being donated to a water molecule. And so aluminum, Al3 plus, actually acts as an acid and will lower the pH in water. Okay, So those are things you need to know. Where's my pen? There it is. So highly charged, it needs to be +2 or more. Metal ions, metal cations. There. So if any of these things show up in chemistry, the pH will be affected. Hey, and here's carbonate. That's a weak base. How much of it do we get after we react these things together? HCl is a strong acid with a weak base. That's what's happening here. So change the milliliters to liters, divide by 1,000. And then M stands for moles per liter. So multiply them together to cancel out the liters. 0.1 times 0.1 is 0.01 moles of Na2 plus CO3. And really, right, the sodium's a spectator ion. When this dissolves in water, you're just going to get a whole bunch of carbonate ions, 0.01 moles of them. Do the same thing here. Divide this by 1,000, change it to liters, moles per liters. Multiply times 0.1 times 0.05, and that's 0.005 moles of H plus ions coming from the strong acid, HCl. And you can see, if we put another 0 here, you can see that that's like 10 and 5. There's twice as much of this. And so after they react, the H plus is the limiting reagent. So you're going to have 0.05 moles of H bonding to the carbonate to form bicarbonate ions. And then there'll be some leftover carbonate. And the question was, is this a buffer or is it not a buffer? Well, it's got bicarbonate ion in it. And we just said that's essential for life. It is one molecule that acts as both an acid and a base. It's got H. It's an acid. It's got a charge, so it can accept H plus. This in itself, being present, makes it a buffer. Yes, a buffer. And wait, so the question was what doesn't? So don't mark this one. That's how the game's played. And then everything else is pretty much the same. Here's bicarbonate reacting with an acid. Just remember that the old baking soda vinegar reaction, baking soda provides bicarbonate. And then H plus comes, well, from here it comes from HCl, but it could also come from vinegar. And H plus with bicarbonate makes carbonic acid, which is unstable to produce water and carbon dioxide. And these are not buffers. Okay. So anyways, you can do the rest of those now. Number 2. Using the following Ka values, indicate the correct order of base strength. Wait, A stands for acid. And then wants to talk about bases. Okay, so here's how it works. Find the order or ranking for strongest acid to weakest acid. And then look at the conjugate base. We'll show you that in a minute. And then the order flips. The weakest acid is going to produce the strongest conjugate base. And your strongest acid is going to produce the weakest conjugate base. And your ordering flips then. And that's what they want. They want the correct order of base strength. That's the pattern that you need to know. So, okay, we got 5 anions here. We want order them according to base strength. Well, let's switch them back to acids. So we got Cn, NO3 minus, F minus, water, and Cl. Okay, the Cn comes from HCN, and it's right here with a Ka of 10 to the minus 10 approximately. So I'll just say 10 to the minus 10 is the Ka for HCN. HNO2. Oh, I miswrote. Sorry. Gotta be careful. NO2 minus, NO2 minus. Good. NO2. Good. This one has a Ka approximately equal to 10 to the minus 4. Fluoride is HF. Ooh, it's right here. 10 to the minus 4. Ooh, so I better not approximate. I need to go 4 times 10 to the minus 4 and 7.2 times 10 to the minus 4 and ask which one's larger? The 7 times 10 to the minus 4. And of these three then, this one has the largest Ka. That makes it the strongest acid. Right? Bigger the Ka, the more acidic it is. Cool. What's water's Ka? That's weird. The Ka is the same as a Kb, which is equal to the Kw. And do you get that on your exam? I think you do. Yep, there it is, Kw. It's 1 times 10 to the minus 14. Okay, so that's a nice thing to remember for water. The acid constant, equilibrium constant, the base equilibrium constant, the ionization constant is all equal to 1.0 times 10 to the minus 14. So the Ka is 10 to the minus 14. How's that rank in here? This is the smallest, 10 to the minus 14, smaller than 10 to the minus 10. HCl, where is it? Where's the Ka for HCl? In your head. So up here, it said you need to memorize that HCl is a strong acid. What does that mean? It means it fully dissociates. If it was an equilibrium reaction, we'd use a double arrow. It's not an equilibrium reaction. It's 100% products. You could say the Ka is equal to H plus over Cl minus over HCl. That's the definition of the Ka. That's the definition of equilibrium. And in reality, it strongly favors products. So this is a huge number, large, and this number is going to 0. There's no molecules of HCl in water. It goes to 0. And if you divide by 0, the limit is infinity. Okay, so it's actually a huge number. Okay, that's got the biggest Ka. So the Ka is huge. So let's rank these in terms of acid strength. So what is the base strength? Maybe we should start with that. We got the strongest base on the left. Okay, so let's put the weakest acid on the left and go to the strongest acid on the right. And the strongest acid using Cl is HCl. That's a huge Ka, strongest acid. What's the next largest number? This one. HF has a Ka of 7.2 times 10 to the minus 4, followed by 4.0 times 10 to the minus 4, HNO2. And then, do we get them all? 5? Yeah. And then the Ka for Cn is small, HCN, 10 to the minus 10, but water is even smaller than that. Water is the weakest acid. And so now you flip it. Wait, this is weird. Why is this over here? That's not your weakest acid. This one's weird. It is the weakest acid, but when you switch it, sorry. You're supposed to then go from the acid to the conjugate base. Conjugate base. The conjugate base of water is hydroxide ion. And you got Cn minus, NO2 minus, F minus, and Cl minus. And the strongest acid produces the weakest base. And this one's going to be the strongest base. Hydroxide's even stronger, but hydroxide's not in this table. Water is. So you need to use not this molecule, but water again, which has a Kb of 10 to the minus 14. Where does it go? It actually goes here because Cl's Ka is going to 0. even smaller, tiny, less than 10 to the minus 14. Here's another way of thinking about it. You dump in, these are bases, water's a weak base. Dump in some HCl into water, what's gonna happen? Let's just dump in some H+. Add some H+ to water, you will make hydronium ion. Cool. Add some H+ to chloride ions. You don't make HCl. HCl is fully dissociated. It doesn't reverse. This is just not a base. Another idea, put some NaCl in the water. What's the pH? Wait, this is just salt. It's neutral. Yeah, because Cl- does not grab any H+. It is not a base. Water is a weak base. It is more basic than chloride ions. So that's why we have to put it here. Cool. And then what we got? We got Cn- by NO2, Cn- by NO2, that's letter A. Then F, water, Cl-. Cool. Nice. Okay, number 6. I wish I would have written a little more clearly. Maybe it's not too bad. Let's go cut and paste something here. Our list of stuff we're supposed to memorize. Yeah, this. Control C that, and we'll Control V it down here. There we go. Okay, so we're supposed to know that for question 6, using the following choices to describe an aqueous solution made from each of the following substances. Do you want to know if you mix sodium nitrate into water, do you get an acidic solution, a neutral solution, a basic solution, or do you just throw in the towel? Don't throw in the towel. No, it's not that one. We can figure this out if you know this information over here. Okay, sodium nitrate. Is nitrate one of the basic anions? It is not. Hydroxide, sulfide, phosphate, and then a bunch of C's, carbonate, chromate, oxalate. Nitrate's not on the list. This is neutral. It's not a basic anion. And sodium, it's always a spectator. It doesn't do anything. That's neutral too. So we expect that solution A, putting some solid sodium nitrate in the water, is going to result in a neutral solution. It's not going to change the pH. What about chromium? Ooh, what's that Roman numeral mean? It means chromium's a +3. Scroll down a little bit. That's a highly charged metal ion. I forgot to finish my thought here. Highly charged metal ion, +2 or more. Chromate's a +3. This is acidic. Let's double check that chloride's chloride's not going to do anything, right? We just finished talking about how chloride is not a base because it's a conjugate base of a very strong acid, HCl. Carbonate, ooh, that's right here. That's a basic anion. That's going to make a basic solution. There you go. That's the plan. For the mixed salts, meaning you have a cation and an anion that could each change the pH, well, do we? NH4 is the ammonium ion. Ooh, it's right here. It's an acidic cation. So the pH should go down, lower pH for the acids. And then we have acetate. Why is that not on the list? Darn it, it should be. Darn, acetate, what are you all about? Well, it comes from acetic acid, which you've seen in other ice tables. Thought I had them all, I don't. Acetate, C2H3O2 is an acidic anion. It comes from a weak acid, so it's HCN, Cn-. So all the weak acids that we've seen already, if it sets up an equilibrium, then this is a weak base. So it's really helpful that they gave us the KB and the KA. A stands for acid, B stands for base, you know? Okay, maybe that's why this is here. Phew! So I'll do that on the exam too. I'm expecting you to have these memorized, these 6. And for others, I better supply the KB. They'll clue you in. Say, hey, wait, acetate is a base. Ammonia is an acid, although I didn't have to tell you that to identify it. That's one of the ones you should know. On the other hand, well, the ammonium ion is trying to lower the pH as an acid. Acetate's trying to raise the pH as a base. Who wins? They dead tie. This is not a very strong acid, and comparably, this is 10 to the minus 10 versus 10 to the minus 10. This is not a very strong base. This is still neutral. But if we look at this one, we got the ammonium ion, 10 to the minus 10, and we got, what is this, chlorite. Chloride ion is a base, 10 to the minus 13. Ooh, that's even weaker. This is just a little bit stronger. So because the Ka is bigger than the Kb for this molecule, the Ka dominates, and the solution will become weakly acidic. It'll be a little bit below 7. That's how you play that game. Cool. So memorize this list, get comfortable with it, and you'll be fine. Titration. Okay. Consider titration of 100 milliliters of a weak diprotic acid. Okay, diprotic means 2 protons. A proton is a proton is. It's the component of the nucleus. If it had an electron, it could make an atom, a hydrogen atom. But if you don't have an electron, then H plus is a proton. And there's 2 H pluses that could be released by this molecule, making a diprotic acid. All right, and then we're gonna have a solution of this, probably Erlenmeyer flask. We got the H2A, and then in our burette, hopefully you've had a chance to do a titration before. We're gonna fill this up with NaOH. There's a concentration of it. Start dripping it in, and we'll have an indicator here, or no, we're not. Maybe a pH meter or an indicator. It doesn't say how we're doing the titration. Just start adding some of the titrant, NaOH, to the acid, and we'll see what happens. They want us to predict the major species. Okay, sorry for that weird word choice. Species just means either a molecule that's neutral, or an ion that's positive, or anion or negative. That's it. So what is the major thing? Major molecule? Well, ions technically aren't molecules. They need a counter ion to neutralize it. Anyways, let's not be technical. It's just asking what's the major thing in here. Water is always assumed to be a major species, so don't talk about water. Choose one of these 5 choices. Okay, so it's the start of the reaction, titration. You only have HA, and it's said to be weak. So sure, it sets up this equilibrium. And then this, it says it's diprotic, so that molecule can set up this equilibrium. But they're weak. So does that favor reactants or products? Favors reactants. And if you don't make much of this, you really don't even have to think about this equilibrium. This is the major component. You would just choose D. The major species, the solution is essentially mostly H2A, the original acid, diprotic acid. Ooh, but now you had 25 milliliters of 0.2 molar. So change that to 0.025 liters. This is 0.20 moles per liter, and we multiply to cancel out the liters. And we'll find out how many sodium hydroxide we added. I got the calculations over here to save us some time. This is letter B. Yeah. Where's my math? Oh, there it is. Sorry. It's 0.005 moles of hydroxide ion, right? Sodium spectator. And then that's going to react with, well, you start with 100, which is 0.1 liters, times 0.1 molar, that's 0.01 moles of H2A, the diprotic acid. And then we can see our limiting reagent is hydroxide ion. It's going to run out first. So no more hydroxide ion. And what happens when the 0.005, if I put a 0 there, it looks like 10 and 5. So half of this reacts, and hydroxide is a base, removes an H+. So we're going to make that molecule 0.005 moles of it. And then the leftover part, it's the excess reagent. You still have some H2A, 0.005 moles of that too. Oh wait, they're equal amounts. They're both equal components. That's letter B. So you'd say these are your two components. You don't have any. Oh, that's all you have to do. Yeah, that's all you have to do. Those are the two major components. Hey, and this is an interesting point here. You have equal amounts of those two. You have equal amounts of original acid and its conjugate base. So at the top of the exam, we have the Henderson-Hasselbalch equation right here. And we just said we have for the HA minus, and this one is the H2A. We have 0.005 moles of this one, and we can divide by the liters to get the volume. Doesn't matter, you can use moles in here in the Henderson-Hasselbalch equation because the liters are the same for both of these and they cancel out. And 0.005 divided by 0.005. So this number divided by that one's equal to 1. So then we're going to have pH is equal to the pKa plus log of 1. And the log of 1 is equal to 0. And whoa, measure the pH right now, and you actually have the pKa. And the Ka, if you know the pKa, is 10 to the minus that value. Okay, so that's an equation you should know. Hopefully you already know that pH equals the negative log of the H plus concentration. And that if you want the H plus concentration, you just undo this one. You raise everything to a power of 10. And then it doesn't matter if it's pH, it could be pKa. The equation looks the same, right? So 10 to the minus pH is like 10 to the minus pKa. You get the Ka, you get the H. Cool. All righty, I think we got enough of 8. Just keep going. You can figure out, do this limiting reagent problem. You can figure out what you need and find out what the major components are. Look at the products. Oh, one side done. Let's take a look at the other side. Calculate the pH of 0.5 molar solution of aniline. What the heck is that? Oh, here's the formula. Ooh, but more importantly, it's a base. So C6H5NH2 has a Kb. It's a base. So what do bases do? They accept H+. From what? Well, it's in solution with water. Okay, so hey, aniline, whatever you are, be the base, take on an extra H. And I'm pointing at the nitrogen because I need an atom to actually make a bond to H+, somebody with a lone pair. So we had to memorize our weak acids and bases over here. So cations that have a nitrogen positive charge, extra H, those are acidic, and they can release H+. So the nitrogen has a lone pair and can be a Lewis base, electron pair donor. But more importantly, it can just be a base, accept an H+ from water, and become C6H5 and H. Well, not 2 of them, but 3 of them now. and it took on an extra H plus, so the plus charge is still there. You can put it here or on the nitrogen. Water served as the acid, so it donated away an H plus. So oxygen, you had two H's, not anymore. You only have one H, and you now have a negative charge. And whoa, with hydroxide ion being produced by this molecule, the pH is going to go up. It's more basic. All right, we want to measure the pH. Well, keep going with your ice table. The initial concentration is 5 molar. You don't use this as a liquid, so ignore that. And then you don't start with anything initially, and you don't start any, well, technically you got 1 times 10 to the minus 7 molar because it's water, but that's such a tiny amount. We're just going to assume it's approximately equal to 0. How does this change? Well, this is not at equilibrium if you have 100% of this molecule. It needs to shift to the right. So you're going to lose some of this molecule as it dissociates. No, as it reacts with the water, it grabs an H plus. You're going to lose one of these and make one of those. That's an X. And you're going to make one of these. And so that at equilibrium, it's going to be 0.05 minus X, X and X. Cool. That's equal to our KB. It's going to equal the products, C6H5 and H3 plus times hydroxide ion, divided by reactants, this molecule, and then this one, oh wait, so it's a liquid, doesn't enter the equilibrium expression. KB is 3.8 times 10 to the minus 10. These two are x's, so x times x is x squared. This number is the original aniline molecule. It's 5 minus x. And let's use the approximation. It's a very strong, sorry, it's a very weak base. So x is going to be small. If it's a weak base, it doesn't pick up H plus very often. We're not going to have very many of these things. It's going to be a little bit, a tiny number. X squared over 5. Cool. So then I'm not going to show the math. You've done the, multiply by 5, take the square root. X for number 13 is equal to, well, I got 4.36. No, 359 times 10 to the minus 5. And what do I want? I want the pH. Well, this is the concentration of this molecule and hydroxide. Ooh. There's a hydroxide ion concentration, and we know the H plus ion concentration times hydroxide is always equal to Kw. If you don't know it's 1 times 10 to the minus 14, you can go look it up at the top of the exam. It's right here. The Kw is 1 times 10 to the minus 14. Cool. So 1 times 10 to the minus 14. This is that 4.359 times 10 to the minus 5. And this is our unknown. So divide this out. And then for the pH, negative log of your H plus ion concentration, I got, oh, I used the POH. Well, where is it? Oh, there it is, 9.6. So sorry, I didn't show my math. But see if you can crank out the math to get 9.6 as the pH. As a self-check, we know it's a base, so our answer better be larger than 7. And it is 9.6. Okay, calculate the pH of the following aqueous solution. Okay, what do we got here? We got carbonic acid. That's okay, that's a little weird. That's supposed to dissociate and fall apart to form water. and carbon dioxide, but all right, we'll just run with it. It's a diprotic acid. The first hydrogen comes off with a pK value of 6.37. The second hydrogen comes off with a pK value of 10.25. Okay. We want the pH. That's what we want. We want to know, let's get more room here. There we go. Okay, so we want pH. Really, we want the hydrogen ion concentration from an ice table. We got this number. Sorry, we got this molecule. So it's going to just dissociate all by itself to form some H+ ions and bicarbonate. And then sure, bicarbonate could fall apart again. But it's pretty tiny. This is, the pK values. Remember, these are logarithms. And if you don't see that, hey, let's undo it. Let's calculate what is the, I need more room. Didn't plan this out very well. Here we go. What is the Ka, or the first Ka? I got the pK of it, so 10 to the minus pKa will give me that value. It's 10 to the minus 6.37, which, where is it? This is number 14. I got 4.27 times 10 to the minus 7. And if you do the same thing with the second Ka, raise it to the power of 10 to the minus pK value, minus 10.25, then you get 5.62 times 10 to the minus 11. Yeah, this is a much weaker acid, 10 to the minus 11. 10 to the minus 7 is bigger, it's a stronger acid. So let's only worry about the pH from this equilibrium. Okay, so we start with 0.50 molar of this stuff, and we don't start with any of this. And I know 10 to the minus 7 moles is actually coming from moles per liter. 10 to the minus 7. That comes from water, but it's such a tiny number, it's approximately equal to 0. What's going to happen? It needs to shift to the right to set up the equilibrium, get some of these molecules because it has none. So some of this molecule starts dissociating, produces some some H+ and some bicarbonate, and at equilibrium, we're at that equilibrium concentrations, and wow, the math is going to be the same as before. Just what we did in 13. You're going to say Ka1 is equal to your products divided by your reactant, and we got 4.27 times 10 to the minus 7, and we have x squared on top. That's an x. This bicarbonate's an x. And on the bottom, it's 0.5 minus x. I'm going to assume that's equal to, it's going to be small, so this is approximately 0.5. Yeah, so multiply by both 0.5, take the square root, x, number 14, I got 4.62 times 10 to the minus 4. And that is your H+ concentration. Are we done? No, we need the pH. So you get lots of partial credit, probably only missing 2 points. If this is like an 8-point problem or 6-point problem, we got most of the work and points already. The last thing is you need to remember that the pH is the negative of the log of the H+ concentration. So negative log of that number, 4.62 times 10 to the minus 4, should be around 4, 3 or 4. Put in your calculator, and the pH turns out to be 3.34. Cool. Does that make sense that it's below 7? Yeah, because this is a pKa, an acid, it should be lower than 7. Nice. More buffers. Okay. You have solutions of 2 molar HNO2 and 0.2 molar KNO2. And the Ka, ooh, okay, the acid, wait. You kind of knew it was already an acid. Remember that chemists like to put the H first in chemical formulas of molecules that are acids. And this is not one we recognize. Well, it's pretty close. Nitric acid is a strong acid, but this one didn't make the list, so this one must be weak. Oh yeah, the Ka is less than 1. It is weak, 10 to the minus 4. Anyways, I went off on tangents there. Hope that was helpful. A buffer of pH 3 is needed. Okay, what volumes of these two liquids are required to make a 1 liter solution that's buffered? This is a real problem. You might actually do this in a bio lab, right? If you're going to set up a cell culture, make life possible in a test tube or on a petri dish, you got to give it a buffered environment so that someone doesn't breathe on it, literally, because there's carbon dioxide in your breath, which can dissolve in water to form carbonic acid and lower the pH. Wow, you got potent breath there. You can kill organisms if they are in an unbuffered system. Yeah, so you need to make a buffer to do your cell culture, and that's a real thing. They're on the shelf in the biolab are these two components. Your teacher says, hey, we need to set up a buffer at pH 3. What do you do? Set up an ice table. That's what you do. Okay, you also grab the Henderson-Hasselbalch equation. So slide up and over to the top of the exam. You don't have to memorize Henderson-Hasselbalch, but if you're a bio student, you're going to see it lots and lots. Here it is. pH equals pK plus the log of the anion over the acid. The conjugate base is on top. Let's put this here. There we go. Okay. Whoops. pH equals pKa plus the log of A minus. It's okay. No, I'll put it in there. I was going to say, can I be lazy and leave out the bracket? If you did on the exam, we would not take out points, as long as you use concentrations. Okay, we want it to be really close, 4 sig figs, pH 3. The pKa, well, let's go calculate it. We got the Ka, and remember that pH is the negative log of the H plus concentration. So use this equation, but change your H's to Ka's. Okay, so no H, it's a Ka. No H, it's a Ka. And you can drop the brackets. There we go. So take the negative log of 4.00 times 10 to the minus 4. And that equals number, what are we on, 18? I got 3.398. It's already close. So that's important. Your best buffers will have Ka's, pKs that are already close to the pH that you want. If you choose an acid, a Ka that's far from the pH of your solution, it's not going to be a very effective buffer. Okay, so the pKa, you know, it's too bad it wasn't exactly 3. That would be perfect, because then you know, just use equal mixtures, equal concentrations, and that's your buffer. If the pKa was equal to 3 exactly, but it's not. It's too large. We need to bring it down. So we need this number to become negative. Or in other words, we need the denominator to be bigger. If you don't like the math approach, here's another approach. The pH is supposed to be 3 and the pKa is above that pH. We need to lower the pKa, make it more acidic. We need more acid. So we already know that we're going to use more of this component than this one. You need both. A buffer has both a weak acid, HNO2, and a weak base, the NO2 anion. And because we know it's a weak acid, the conjugate base is also a weak base. That was not one of the ones we had to memorize. But we didn't have to, because we're already told It's part of this equilibrium. This is the acid, and it will have a conjugate base. That does equilibrium, that acts as a base. Okay. I'm more expecting to be more of this than that one. Let's find out how much more. And if you want, you can change out the A minus because we know it's this molecule. It's the NO2 minus. What is that? Nitrite. It's nitrite. And then nitrous acid, I think that's the name of this thing. HNO2 is down here. Okay, so subtract this from both sides. It's going to be a negative 0.398 equal to the log of that thing. 2 minus over this thing. You raise everything to the power of 10. That'll cancel out the log. And then multiply this side to the other side. So get your calculator out. This turns out to be pretty close to 0.4. It's actually equal to 0.4. Weird. Okay. So 0.4 times the HNO2 concentration will give you the concentration of the NO2 ion. Ion. Okay, so you need a lot of this, and you only need to calculate this. You multiply this large number by 0.4 to get a smaller amount. Yeah, so we need more of this. Okay, so what do we do? Then, now we have to be creative. For me, it kind of starts by saying, well, we need to mix. Well, I can't scroll down too far, otherwise I'll lose these concentrations. So what we'd have to do is we're going to take 0.20 molar of HNO2. It's in a beaker. That's my beaker. And we have another beaker, same concentration of the potassium nitrate. Take some of this out, take some of that out, and prepare our 1 liter solution of buffer. Okay, wait. Once you put some of this in here and you add the other one, this will become more dilute. It will no longer be 0.2 molar. So as we add this, we need to do dilution. And you got your M1V1 equals M2V2. And as a chemist, oh my goodness, we do dilutions all the time. So I don't think I gave you this equation. It's one you need to memorize, especially if you're a chem major. No, I don't see it. So yeah, you need to memorize that one. M1V1 equals M2V2. So I can slide down here because we got the concentrations. Okay, and then on this side, from this point of view, that molecule, it's also M1V1. It's also being equals M2V2. It's also being diluted. Okay, so let's just use this equation on each solution one at a time. So for the HNO2 solution, you start with M1V1 equals M2V2. This is your first solution. This one's your second. So the ones talk about this molecule. What's your concentration of the molecule? The ones talk about this solution. So what's the molarity of this solution? It's 0.2. So M1 is 0.200. How much did you take of the solution? I don't know. That's what I want to find out. And then what do you end up with? I don't know. That's what I want to find out. Well, let's just put in this concentration. That's how much you have to end up with in the final buffer. And how much do you have in the solution? It's 1 liter. So 0.2 times volume of how much you transfer, that'll give you the concentration of HNO2 in the final solution. Okay, I got 2 variables here. So I need to jump over here. What do I have over here? For this solution, we're also going to do M1V1 equals M2V2. The first concentration, it's 0.002 molar again. The volume, don't know. That's what I need to find out. How much do you take out of this? Final concentration, still don't know. You could put in this number, but you know what? Looking ahead, I'm going to say this concentration, the final concentration, is supposed to equal 0.4 times this one. More room, please. Times the volume. Well, the final volume of the second solution is 1 liter again. So let's multiply this out. You got 0.200 volume 1 equals 0.4 times the HNO2 concentration. Let me check my notes. Did I find a shortcut somewhere, or do I just have to keep solving? No, that's it. So what do we got? So we got, let's just solve for V1. And let's change this to an H plus. And let's change this to an A minus. So I know which one's which. So I got the volume of the, what was it doing? The nitrite solution, that's my A minus. And I also have my volume of my acid, the H plus. So the volume of the H plus solution is going to be, well, divide by 0.2 is the same as multiplying by 5. It's 5 times the acid solution. And the volume of your base, the nitrite, is going to be, well, divide by 0.2. So 0.4 divided by 0.2 sounds like 2. Looking at my math over here, it is. Okay, and then how do you connect these two together? Well, the trick is, look at my notes, there's a trick. The volumes have to add up to 1 liter, have to equal 1 liter. So the volume from the acid plus the volume from the anion, the base, has to equal 1 liter. So you need the volume to be 5 times the volume of the first thing, the acid, is this, 5 times that, plus 2 times HNO2 equals 1. This is going to be 7 equals 1, and the concentration of HNO2 is equal to be 1/7 molar. You can put that in calculator and get to a decimal. Okay, so now we can go back here and say, okay, the concentration is 1/7 molar multiplied times 5. This is supposed to be in liters, right? The units of volume is in liters. So it's 5/7 of a 5/7, sorry. There it is. 5/7 of a liter, and that's equal to 0.714 liters of HNO2 solution. Plus, well, you put in 1/7 in for this number. Here we go. So over here, put in 1/7, and we get 2/7 of a liter, which is 286 milliliters of the KNO2 minus. Well, KNO2. That's how much you have to mix together. Whoops. Point. I changed the milliliters, sorry. That is correct. 286 milliliters, or it's 0.286 liters, 1/7 of a liter. Liter. Wow, I need to take a break. My brain's not keeping up. That was a really hard problem. But it's a really important one, though. It's how you would actually go into the biolab and prepare your cell culture. All right. This one's easier. 19. Write balanced chemical equations to show a buffer composed of ammonium acetate. What the heck is that? You have to memorize your polyatomic ions. So the ammonium ion is this molecule, NH4 plus, acetate. Actually, we saw the chemical formula of that earlier, C2H3O2 minus. And then you make sure that the charges cancel, and they do. So the ammonium acetate has this formula. There's ammonium acetate. How is that a buffer? And then show balance of chemical equations, how it neutralizes H plus and OH minus. So you need two equations. You need to show that, well, we got this buffer with these two things in it. How's that a buffer? Well, this one is an acid, and this one comes from the weak base, acetic acid. Let's move this out of the way. And so it's a weak acid, sets up equilibrium like this. And then what can we say about this molecule? Well, sometimes the reaction reverses. So this plus that goes back to this. Wait, what does that mean? It means this is going to accept this H plus and reform the acid. That makes it a weak base. So we got a base, we got an acid. Hey, that's a buffer. We got two weak things, a weak acid and a weak base. It's a buffer. Okay, so those are two things. Which one was a buffer do? It prevents the pH from changing. Well, it tries to resist it. It changes it a little bit. H plus is trying to lower the pH. Attack. Attack with what? The acid or the base? The base. So the buffer sends in its base to attack the incoming H plus. And then just use your knowledge of chemistry. What do bases do? They accept H plus. And that's how you predict the product. The product is actually vinegar. Well, the component of vinegar, acetic acid. I guess we should put in the physical states, everything is aqueous. Is it balanced? Yeah, it's balanced. Nice, we got half the credit right there. Okay, and some joker throws in some hydroxide ion into our buffered solution. No worries, we'll attack it with one of these things. Which component of the buffer, the acid or the base? Now it's the acid. You need to attack hydroxide, which is a base, with the ammonium ion. And then use your knowledge of chemistry to figure out the products. I don't know. Oh wait, what's the definition of base? H plus acceptor. So hey, you base, you get another H plus. Oxygen, you have one currently. Now you have two of them. And the plus charge, H plus, comes over here and cancel out the minus charge. Yeah, water's neutral. What are you doing? You're the acid, you're an H plus donor. So donate H plus. So as the nitrogen holds on to 4, it lets go of a hydrogen, so it keeps 3 of them. And that hydrogen it leaves takes away the plus charge. And so now you have neutral ammonia. The physical state of water in solution is a liquid. NH3 is the AQ, the ammonium ion. Your cations and anions are going to be aqueous. And we're done with number 19. Yay. 22. Use the following graph to answer the following questions. Let's put that, I don't know. Guess I have to keep here. It's in the way though. No worries. Where's the equivalence point? What the heck is that? Equivalent, what's equal here? Well, what is this thing? The x-axis talks about milliliters of HCl. What's HCl? Strong acid. Y-axis, we're looking at pH, and the pH is changing, and it's coming down. As you add more acid, oh yeah, that makes sense. More acid's going to lower the pH. You must have started with the base in solution. The pH meter was in a beaker or something, or a Lamar flask. Measure the high pH of 12. We inputted some HCl and the pH starts coming down. This is titration. Start with the base, add an acid, you're neutralizing it. That's the definition of titration. Equivalence means when the thing's equal, when you have the same number of moles of base as acid. Okay, if you have a strong acid, strong base, and they're equal, if you have a strong acid, all the acid produces H+, there's no other weak acid left behind. The strong base produces all hydroxide ion. So then when they're equal, you make water and the pH is 7. But if you have a weak base and you add in, whoops, weak base. Let's make that A- for acid, for anion. You're going to make HA, which is, if this is a weak base, you make a weak acid, which then sets up an equilibrium where you then have some base and acid. And the pH is not going to be 7. You're going to have more acid, so it should be more acidic, but it's not going to be pH 7. So where is it? Well, it's where this becomes a steep line. That's your equivalence point. So your equivalence point is that just above, it's about 50 milliliters of HCl. That's the equivalence point. That's where the titration should be ending. We're at 50. And it looks like if you go from like, right here to here, if you go halfway, it looks like it's about 4.5. Yeah, that's not 7. But where it goes vertical is where the equivalence point is, where you've had an equal number of base as acid. Cool. Locate the buffering region. What's a buffer? Something that resists changes the pH. So as you add more acid, if it was HCl added to pure water, the pH would be falling very rapidly. But it's not. It's leveling off right here. So it started dropping pretty quickly, but all of a sudden, look, so you added 10 milliliters. It went from pH 12 down to 10. You add another 10 milliliters, and it really didn't change much. Add another 10 milliliters, it didn't change much. Another 10 milliliters, then this is your buffering region. So you start with a base, it's a weak base. You're adding acid, you're making this, and you're setting up the equilibrium. You have both a weak acid and a weak base present right now in the buffering region. And if you have a weak acid and a weak base, that is a buffer. So maybe if you had to write this out, showing your work, you might circle the graph. That'll be hard to do on the computer screen. So you might write in words on your scratch paper that you submit as a PDF. You could say, it's about 10 milliliters. Wow, handwriting. 10 milliliters to, I don't know, about 40. And it's approximate, right? So someone said it's, 15 to 35, full credit. If you said 0 to 50, you would lose points. Right here at 50, it's not in the buffer region anymore. It's starting to fall off rapidly. So yeah, cut off the edges, go for the region that's pretty flat. There you go. What's the bioequilibrium constant? What? Where's this coming from? Anderson-Hasselbalch equation. That's where it's coming from. Did I post it up here? No. Is it over here? No, there's more. Over here. Yes. Anderson-Hasselbalch equation. pH equals pKa. There's an equilibrium constant plus the log of A minus anion on top over HA. Where are we? Here we are. Okay, so I need more space than that. Or do I? Let's find out. Henderson-Hasselbalch equation. We just saw it. You don't have to memorize it. But if you use it enough, it sort of sticks in your head anyways. Okay. Sorry, my problem with the memorization here. pH equals pH. No, it doesn't. It equals pKa. Glad I caught that. What did I not catch? Yikes. pK. Okay, so this is what it wants. It wants the equilibrium constant. And wait, you start with the base. We got to fix it. So we're titrating an acid with a base. Okay, so really, oh, and that's question D. What's the proper symbol for the equilibrium constant? We really want the Kb because we're starting with the base. That's the molecule we're titrating against. Okay, so letter B, the answer is Kb. That's the proper symbol. You start with the base. So we're gonna have to change the Ka to the Kb. We can do that. Let's find the Ka first. So the pH and the pKa, we also need to know these concentrations. Okay, what's cool with the titration curve is at the equivalence point, that's where we said moles of base equals moles of acid. You start with the base, an A minus, and then you add enough acid, so the base, add the acid, and at 50 milliliters, you'll form the conjugate acid of this base. The moles are equal. So at 50, I got an idea where I don't have any A minus, it's all HA, all acid. If I go to halfway, at halfway of 50, so 50 is my equivalence point, halfway is at 25, then I didn't titrate all the A minus, all the base, I've only titrated half of it. So half of it reacts to form HA, and there's still half left over. We have equal molarity, equal concentrations of these, right? So just repeat it, make sure it's clear. At the start of titration, it's 100% base. At the end of titration, it's 100% conjugate acid. Halfway, it's going to be a 50-50 mixture, a 50-50 mixture, equal quantities. So whatever this is, the bottom's the same. This ratio goes to 1, and the log of 1 is equal to 0. And the pH equals the pKa. So go to your halfway point, 25, which is right about here, and do your best way of measuring or approximating that. Well, let's see. This is 10 and that's 8. Halfway is there. That's 9. It's a little bit more than 9. 9.3, 9.5. What did I put in the answer key? This is 22. A little bit more than 9 is the pH. I said 9.5. And if you put 9.3 and 9.4, that's good enough. This, you really can't read much off of this. But it's definitely greater than 9. So at the halfway, pH is, let's say it's about 9.5, and that's the pKa. Oh wait, what does it want? It wants equilibrium constant. So what's the Ka? It's 10 to the minus the pK value, 9.5, which Ka is equal to, I'm really not confident about my sig figs here. Let's just keep it the 1 sig fig. So let's round off to 3. So put that in your calculator and just round off to 1 significant figure because it's pretty approximate. 3 times 10 to the minus 10. Ooh, but the value of the Kb, we should be looking at Kb. So one more step for letter C. Just remember that for acids and bases, if you multiply the Ka and the Kb together, you get the Kw. So the Kb is equal to the Kw over the Ka. And if you go to the top of the exam or sample test, which is over here too, I think. Wow. Yeah, the Kw is 1.00 times 10 to the minus 14. And where was I? Sorry, 22. There you go. So Kw is 1.00 times 10 to the minus 14. The Ka is 3 times 10 to the minus 10. And the Kb, finally, I got 3 times 10 to the minus 5, 1 sig fig. And that's for question C. Question E, which indicator would be appropriate to use? Okay, so we need a color indicator, something that changes color at the equivalence point, and the equivalence point looks around 4.5. So as we're adding the HCl, we want the color of the indicator to be the same, and as it drops here, we want the change. It says, hey, stop adding. So at 4.5, we want to change color and stop adding HCl so we know the titration is done. So we need an indicator that changes color at 4.5. So go to the top of the exam, because that's where some indicators are listed, I hope. Yeah, this table right here. Indicators and pH range of color change. So we need something to change at 4.5. Ooh, this is changing at 4.5. That's not good. Maybe we should use this one. Yeah, this would be a better one. Let's use methyl red, because 4.5 is inside this range. If someone said methyl orange, I would give you full credit. Technically 4.5 is at that's where it's changing. It's changing color between 3.3. Yeah, you could do either one. I prefer to have the pH in the middle of the range, ideally. You lose points if you chose one of those. Those are outside the range. Yeah. Whoa. Cool. All right, so that was 22. Methyl orange or methyl red for the indicator. Phew, okay, so that's the end of the section with acids and base. And you know what? This video is getting long. So for more examples, see the Chem 6 sample test video. On exam, I think it's theirs is exam 4. So I go over entropy and enthalpy, Gibbs free energy, delta G, some of the questions that I used in my introductory course of Chemistry 6. I just thought I'd just check and make sure you guys knew those same concepts. So I put those questions in the sample test. So take a look at that video, and that'll kind of break up this one, make it not so long, and I don't have to repeat myself. All right, so let's do a couple of these energy equations using delta G. 42, for the reaction of this thing, we have delta H. That's heat of reaction. It's also the enthalpy change. Enthalpy has an H in it. And what's the algebraic sign? Is this a positive or a negative number? It's a positive number. So looking at delta H, we can decide if it's exothermic or endothermic. And so what I tell my students is, well, think of an exothermic reaction, like a fire, definitely exothermic, heat's coming out, and now be the fire. I am the fire, I'm burning, and I'm turning to ashes, and I'm losing all my energy because energy is exiting me. I am exothermic, and I lost it all, so I'm losing energy. Exothermic reactions have a negative delta H. This is positive, meaning it's the opposite. Heat is entering endothermic. This is an endothermic reaction. That might be useful. S, it's not enthalpy, it's entropy. It's a measure of disorder. What's the minus sign mean here? It's not that disordered. So as entropy increases, things become more random, more chaotic, more crazy. If it becomes more negative, it becomes more ordered, put in place, nice and neat and regular. Yeah, so it's becoming negative, meaning more ordered. That's not the way the universe likes to run. Things just tend to make a mess eventually, become more random. All right, overanalyzing this, sorry. What do we want to do? We want to calculate delta G. So let's go see if we get an equation for that. We got 3 of them. There's a delta G, a delta G, a delta G. If we look at this one, it's got a Q in it. That's a reaction quotient. That's for an equilibrium reaction that's not at equilibrium. Okay. K, well, that's equilibrium constant. So now we are at equilibrium. And then over here we have delta H and delta S. Oh, wait, that's what was in the question. So let's use this equation with delta G in it. Even though it doesn't have the little degree symbols on it, that's okay. You can put degree symbols on everything and it's equivalent. So the little delta, the circle means standard. It's like, you know, the kind of the systematic form. So if I copy it over, it was over there on the right. We want delta G and we're given delta H. It's a positive 126.4. Ooh, pay attention to the units because sometimes they don't match. Minus temperature. Oh, it's right here. Ooh, but you also have to remember that this temperature must be in Kelvin. Do you have to remember 273 or do I give that one to you also? Yeah, there it is. Cool. Remember to convert. So add 273.15. Okay, whatever. Or sig figs. Okay, so the temperature is going to be 377 plus 273.15. You got to change it to Kelvin. And then the entropy term is a negative 74.9 joules. This one's kilojoules. So we're going to have to change our units per mole Kelvin. And after that, you just, you know, convert your unit. Oh, let's just see. What did I do in my answer key? This is 42. It's all math now. You're missing 2 points. You have to convert either the joules or the kilojoules to make the units match. And you have to put numbers in your calculator. You got most of the points already. Nah, I didn't do it in the answer key. So, sorry, this video is getting long already. I got 175 kilojoules per mole. So this one, you have to multiply that together. And then let's get rid of joules and go to kilojoules. So you'll have to cancel out the joules. And how many joules in a kilojoule? Well, think about how many meters are in a kilometer, or how many grams are in a kilogram, because that's the same as the joules in a kilojoule. It's 1,000. Yeah, so 1,000 joules is 1 kilojoule. So add these together, multiply, multiply. Ooh, that's a minus, that's a minus. These become plus. Yeah, and then add it to 126.4. You should get 175, 3 sig figs. Yeah, the temperature and the S are in 3 sig figs. 44. Okay, so on the sample test, I know there's question number 44, but what I did is I merged 2 old sample tests together and I deleted a whole bunch. So there's like no, there's a bunch of problem number 30s that have been deleted. I think there's only 24 questions total on the sample test, so not 44 or 45. But there's a problem with the number 44, and that's this one. Anyways, determine delta G for the weak acid, Kf, and we have an equilibrium constant. Oh yeah? Well, let's go find an equation with the G and a K in it. Yeah, that one right here. G, delta G equals negative RT ln K. G equals negative RT ln natural log of K. Cool. You want that. All right. And that delta G is going to equal negative R. I don't think you have to memorize that one. There it is. It's right at the top. It's 8.314 joule mole Kelvin. 8314. 8314. There's a point here. There's joule mole Kelvin. Times temperature. Do we have a temperature? Well, in Celsius we do. So if they add 273, which is 298, if you want to put the 15 in there, you can. That's what the number is on the top of the answer of the exam. And then natural log of the K, which is 7.2 times 10 to the minus 4. Not 14, oops, 4. Yay, so we get all the points except for one. You get one more point if you punch in your calculator and you get 175. Wait, that's 42. 44. 1.8 times 10 to the 4th joules moles. Why 2 sig figs? Oh, because there's 2 sig figs there, maybe? 2 sig figs here. Is there one left? There is. Okay, number 45. At 699 Kelvin, thank you. I don't have to convert from Celsius this time. Delta G is that number for this reaction. Calculate delta G. Wait, the standard temperature, the standard free energy is already given. Where's the little degree sign? Well, this isn't the standard. This is probably not at equilibrium. When? So calculate delta G for this reaction if the reagents are both supplied at 10 atmosphere pressure and the product is at 1 atmosphere pressure. Okay, so to tell us what the pressures are, because these are gases, if they were aqueous, they would have told us the concentrations. And because the little degree symbol is missing, I don't think this is at equilibrium. If it's not equilibrium, this is not going to give us equilibrium constant. It's going to give us the Q, the reaction quotient. So remember, at equilibrium, your equilibrium constant equals products over reactants. Not at equilibrium, we say you have the Q, the reaction quotient, that's still equal to the products over the reactants. Yeah. Okay. We want the Q. We don't know if that's at equilibrium or not. Where is it? It's up here. Okay, so we want the Q, this equation with the, oh, and this is nice. It's got the regular G and the degree symbol on this G. Nice. Okay, so the regular G followed by degree symbol and a plus RTL and Q. It's the regular G, degree with the symbol, a plus RTLN of Q. All right, so you get points for correctly identifying that. wants us to calculate this delta G, and then the standard free energy is a negative 23.25 kilojoules, plus the R, that was 8314, I think. Ew. Joule mole Kelvin, times the temperature. What's our temperature this time? Yay, not in Celsius, it's 699. And then our Q, ln of, okay, got to get the products. That's HI. What's our HI pressure? Product, 1. Okay, so the pressure is 1, and we have to raise it to the power 2, right? The coefficient is your exponent. Guess it wouldn't matter if we forgot. 1 squared is the same as 1. But you know what? Show your work so you can get a point for doing that, or a half a point, because that's the correct way to calculate the Q and calculate the K, right? Use the coefficient as an exponent. Reactants go on the bottom. They're both at 10 atmosphere. And no coefficient, or it's a 1. But yeah, the exponent then is a 1. Awesome. So we get all our points so far except for 1. One more point to earn by multiplying this out using the ln function on your calculator correctly. And what are you going to get? 45. I got negative 50. I kept 3 sig figs. There we go. Okay. I hope that was helpful. Wow. Looking at the time, that was a long video. Pause it. I should have warned you, pause it at certain times, you know, or zoom. Fast forward it to the parts of the test you want to look at. I hope that's helpful. Good luck on your exam.